study of the universe spans almost inconceivable extremes of size and distance and time. The vast island of stars we call a galaxy, to the tiny atom and the particles that comprise it. From cosmic events that occurred billions of years in the past, to microcosmic events in the present that endure for only billions of a second. To explore the universe at these extremes, the scientist builds instruments that extend his reach and his vision. His great telescopic eye has the light-gathering power of 1 million human eyes. It peers not only into the depths of space, but far back in time. Since the light it now observes may have left its source when dinosaurs inhabited the Earth. His telescopic ear is tuned to the invisible radio sky. It detects not objects, but the radio regions associated with them, and at distances far beyond the range of the largest optical telescope. But the radio waves and the visible light that pass through the Earth's atmosphere to these ground-based telescopes are only part of a broad spectrum of radiation, most of which is blocked by the atmosphere. So electronic instruments are lifted above this murky and turbulent layer. Airborne by rockets, by balloons, in unmanned astronomical observatories, in manned laboratories, and in spacecraft orbiting the planets. Instruments probe the near and distant environments of space and open new windows on the universe. Concentration of elementary particles. In one gigantic detonation, the contents of this cosmic fireball were hurled outward in all directions. After 1 million years of expansion, the universe was an intense blaze of light. Then the radiation cooled. And after hundreds of millions of years, great clouds of hydrogen gas began contracting, and in time, evolved into the galaxies we now observe. Inside these galactic whirlpools, smaller fields of gravity condense hydrogen into stars. Stars are inconceivably hot. So hot, they sustain thermonuclear reactions that transform hydrogen into heavier elements. Sometimes their hydrogen fuel burns so fast, they flare out in violent explosions, hurling new elements across space. Like a great wind, the radiant energy of starlight drives these clouds of dust and gas throughout the galaxy. Out of these clouds evolve new generations of stars. More than half the stars in our galaxy travel in groups of 2 or more, orbiting around a common center of gravity. Like galactic comets, immense clusters clusters of stars swing in and out of the galaxy in vast, eccentric paths. Some small stars do not travel in the company of other stars. Our own sun is one of these. To the astronomer, the sun is a vast laboratory for the detailed study of a star's structure and energy. The vertical tower of the solar observatory supports a heliostat mirror which tracks the sun, gathers its rays, and reflects them down a light shaft that extends 300 feet below ground. At the end of the shaft, the rays are cast back to an observing room where minute-by-minute changes across the face of the sun are observed. Another mirror projects a light beam to a spectroscope, an instrument which splits the light into its component colors, a visible spectrum. The dark lines that cut across the spectrum band are produced by the radiation from the sun's interior shining through its atmosphere. Each line is the signature of a chemical element such as sodium, iron, calcium. It is this array of lines that forms the code which describes the properties and motion of a star. By narrowing the view of the sun to a single line of the spectrum, each level of the solar atmosphere can be photographed, and each reveals a remarkably different aspect. And with the addition of computer mapping and color processing that distinguishes levels of brightness, a detailed and multidimensional picture is obtained of a sun undergoing dramatic and turbulent change. The sun is a sphere of hot, seething gases and surges of radiation. Most of the light we get from the sun comes from the thin, bright layer which defines its visible edge, the photosphere. Above it, the chromosphere, a region of flaming outbursts of gas, extends through a transition zone to the thin outer atmosphere of the corona. Once thought to be a quiet layer of the solar atmosphere, the corona is now revealed to be a region of dramatic large-scale changes and unexpected turbulence, with temperatures reaching millions of degrees. Deep beneath the sun's atmospheric shell is the core, a violent nuclear furnace. Here, hydrogen is fused into helium, and in the process, some of the matter is converted into an enormous amount of energy. Radiating outward as a gas, it convects like a boiling liquid beneath the surface. The turbulent, bubbling motion is visible in the granular cells of the photosphere. Sunspots, regions of intense magnetic fields, appear on the surface, disappear in a few hours, or grow and persist for months in a mysterious 11-year cycle. The sun rotates once in 27 days. Because its equatorial regions rotate faster than the polar caps, the shearing action in the gas contorts the magnetic field into tangled structures which give rise to the sun's eruptive action. Shaped by these magnetic fields are the spectacular prominences, titanic streamers of gas reaching heights of more than 500,000 miles above the surface.